Why is multi-physics model integration difficult in engineering? Imagine trying to fit pieces from different puzzles into one picture. Each piece is from a different puzzle, with its own shape and style. That's what multi-physics model integration feels like in engineering. It involves combining different physical phenomena like heat, motion, electricity, and fluids into one simulation. The challenge is that these phenomena interact in complex ways, and each has its own set of rules. To make a good model, you need to make sure these rules work well together, which is not always easy. Every physical domain in engineering has its own way of being described mathematically. For example, fluid flow is often modeled with methods that look at how fluids move through space, while structural mechanics uses different methods to see how materials bend or break. When you try to connect these, the data exchange becomes tricky. You have to make sure the information flows smoothly between models, or the simulation can become unstable or inaccurate. One big problem is that the tools used for different physics are often built separately. They have different formats, ways of dividing up the space into small pieces called meshes, and algorithms for solving equations. This makes it hard to get them to work together without a lot of extra work. Engineers need to develop ways for these tools to talk to each other, which can take a lot of time and effort. Another challenge is that physical phenomena influence each other in nonlinear and time-dependent ways. For example, when electrical currents generate heat in a device, that heat changes how the device behaves mechanically. To capture this, you need simulations that run very tightly coupled, exchanging data at each step. This increases the computational load and makes the process slower. Computational efficiency is also a big concern. Multi-physics simulations requiring a lot of computer power because they solve many equations at once. To keep runtimes reasonable, engineers use advanced numerical techniques, sometimes simplifying models or using faster algorithms. But simplifying can reduce accuracy, so they have to find a good balance. Validating these models is another tough part. It's hard to get real-world data for all the combined phenomena because experiments are expensive and complicated. Without good data, it's difficult to trust the simulation results. Engineers need to test and calibrate their models carefully to make sure they reflected reality. Managing all the data from different physics domains is also a challenge. Automating workflows for design and optimization can be complicated because each physics might requiring different input and output formats. Without automation, the process becomes slow and prone to errors, limiting how often engineers can use these models in real projects. In real-world applications like designing electric motors or electronic cooling systems, multi-physics integration helps engineers see how electromagnetic forces, heat, and mechanical stresses work together. This helps improve performance and reliability. In system control, understanding how different physical domains interact allows for better control strategies and more accurate predictions of how a system will behave under different conditions. All these challenges boil down to the fact that combining different physics requires coordinating diverse models, numerical methods, and software tools into a single, reliable simulation. It's a complex task, but it's essential for accurately predicting how real engineering systems work.